I said that a bike doesn't fall down because its wheels are spinning so fast, you'd probably think that was reasonable. But if I said the same thing about an airplane or a spacecraft, you might think I was kidding you. Well, it just so happens that airplanes in flight and spacecraft do use wheels, namely gyroscopes, which are essential to their navigation and safety. In fact, the stability of rapidly spinning objects has lots of applications. I've always been fascinated by the motion of gyroscopes. The stability which such spinning bodies seem to have never fails to amaze me. My name is Owen Garriott, scientist pilot on the second manned Skylab mission. I'm here in the wardroom of the Skylab simulator at Johnson Space Center in Houston. A great many inventions depend on this steadiness or rotational inertia. Among them are the gyro compass, gyroscopic artificial horizon, and the automatic pilot. In spaceflight, gyro stabilization is just as important as is rocket engines and computers. Spinning gyros establish a stable platform from which the orientation can be measured, even though the spacecraft itself may roll, or pitch, or yaw. Still, its attitude can be established by reference to this internal stable platform. With radio and radar, it's possible to determine the position of a spacecraft from the ground, and with very great accuracy. But the attitude or orientation of a spacecraft has to be measured on board. In the Apollo moon landing project, gyros were used extensively to maintain accurate inertial platforms in the spacecraft. Small thrusters were used to make attitude corrections. Even the lunar rover was instrumented with gyros to assist in its navigation. The Skylab space station also used gyros to establish and maintain its orientation. Small ones to sense changes in attitude, and 3 very large control gyros linked by computer to the small ones to physically keep the spacecraft pointed in the chosen direction. This system of gyroscopes allowed very accurate pointing for our observations of the sun. These were made with a whole battery of instruments located in the Apollo telescope mount. These time-lapse photographs were taken over a period of about 40 minutes, and they had to be taken from a very stable platform in order to see the gas expanding outward through the solar corona or the sun's atmosphere. In fact, no serious solar photography would have been possible without the stability provided by our large control gyros. On the third manned mission of Skylab, Jerry Carr had a chance to demonstrate the behavior of a gyroscope in 0G. Its stability and also its precision when a torque is applied to it can be clearly seen in weightlessness.
Now let me just show you. What I have here is just one of the little hand gyroscopes that you can buy at the dime store. And first of all, I want to show you about what a body does when it's in 0G, and that is when you let it go, it just drifts. Now, if you translate that body, or if you hit it, it moves in translation, and it also tumbles. You notice it tumbles the whole time. And we can hit it in a different direction, and it just keeps on tumbling and moving in the direction you hit it. There's no damping. There's no effort on the part of the body to maintain itself in the position that it was in the beginning. All right. There's my gyro. There's my string, looking to get tangled. Now I'm going to turn this little rascal loose. There. Okay. And I'm going to use these two soda straws in order to provide the forces that I need. Now I've got this gyro spinning quite fast now. And now notice when I hit it with a straw or deflect it, see, it moves in translation, does it? Just exactly the way it did before. But you notice that when I hit it, it doesn't want to tumble or drift in rotation. It maintains its rigidity in space. And this is a principle that's very widely used in spacecraft. Now, remember I told you that the spin axis is up this way, the rotation is this way, and that's the way I've got it set up on this gyro now. Now, if I push on that side of the disc, I expect the gyro to tip this way and show the bottom to you. So let's see what happens if I do that. I also have a little trouble with friction here, wanting to run it off the straws. Now you see what I did? I was going like this with it, but it was precessing 90 degrees from the way that I was trying to get it to go. Now the next thing I want to do is slow this rascal down. Let's try it doing it this way, and get our wheel going a little slower speed. Try to get it going at about half the speed we had initially. All right, I think it's going at about half speed now. Now, I don't know if you can see this very well on your screen, but the spin axis, the very tip where the bearing is starting to wobble a little bit. It's wobbling like this. And we're at a slower speed now. Now what I'm going to try to do is make this gyro stand up again. Now I know that it's spinning this way, and the spin axis is away from you. So in order to make it spin this way, I've got to push here in order to make that part go down. So I'll take it and I'll see I'm pushing on the side, and it's precessing 90 degrees.
There's something about precession that seems just a little miraculous. The fact that the gyro tips in a direction 90 degrees or perpendicular from the way you might expect it to tip. Here on Earth, the force of gravity is constantly acting to tip the gyroscope over. So it's not necessary to apply a torque, as Jerry Carr did with his straws. The rotation that we see here is precession. As the gyro slows down, it has less stability, and also the precession rate speeds up. As it slows down, we can also see its axis tip lower and lower, closer to the horizontal. In space, Jerry was able to demonstrate precession without these pivots, which have a lot of friction, and his gyro therefore maintained a steady speed unless it was disturbed. Now let's take a look at the precession of a larger double gimbal gyro. The friction of these gimbals and pivots is so small that this gyro behaves more nearly like the little gyro in Skylab. I'd like to emphasize that the motions of gyroscopes are straightforward consequences of Newton's laws of motion as applied to rotating bodies. But the precise explanation is a little too involved to get into now. But in brief, we can say that the stability of a gyro or other rapidly spinning rigid body is a consequence of its angular momentum. The law of conservation of angular momentum states that an external torque is required to change either the magnitude or the direction of the angular momentum vector. When you change the direction of angular momentum of a spinning gyro, it precesses, or it rotates slowly in the direction of the applied torque, which is perpendicular to the applied force. Here a torque is provided by pushing against the gyro, as Jerry did in Skylab, or by the steady force of a weight. I hope you noticed that the gyro precessed faster with the heavier weight. Let's take another look at the precession of our little gyroscope in space.
Now, let's slow this thing down just a little bit more. I'm going to try to slow it down so slow that you can almost see the spokes going. You have to be careful not to touch it or you'll end up either tumbling it or with a handful of gyro. All right, now it's going so slow you can almost see the spokes go around. Now, let's tip it again. This time I'm going to try to tip it forward. If I want to tip it down, I need to push here, which means I want to put a force on it. Like so. The spacecraft systems, the Apollo system uses a little gyro like this, a set of them, and it uses these gyros to remember its orientation. What we do is before we spin up the gyro, we set it in a direction, set the axis in the direction that we want to have it go in, and we spin up the gyro with our electric motors, and then that gyro stays there, and it remembers where it is, and anytime our spacecraft drifts away from that attitude, the gyro tells the computer commands the thrusters to maintain our attitude. Now, in the case of Skylab, we also use little gyros like this to remember our attitude. However, when they feed their information to a computer, the computer then feeds information to three huge gyros. And the three huge gyros that we have that maintain the attitude of our spacecraft are 22 inches in diameter. They weigh 140 pounds apiece. The rim thickness right here is about 4 inches. And the speed at which our gyros operate is about 9,027 revolutions per minute. So essentially, the computer sends torques to this big gyro and puts pressure on it. And so the big gyro being connected to our spacecraft precesses and moves our spacecraft in the way we want it to. So, in review, we apply torques to the big gyros, and the big gyros apply a torque to the spacecraft and maneuver it to the position we want it to.
In addition to its gravitational field, the Earth also has a magnetic field, which extends far out into space. Just as a compass aligns itself with this magnetic field, so will a magnet in space, unless it happens to be attached to a spinning object.
The next thing I want to show is when I tip these in a direction perpendicular to that. If it's not spinning, watch what it does. You see it spins right over and turns parallel to the Earth's field so that its spin axis, or its axis through the disk, is oriented with the Earth's field just the way it was before. That's its normal tendency, is to tip right over and align its own dipole with the direction of the Earth's field. Now I'm going to spin it about this direction, and we'll see what its reaction is. All right, now it's more or less spin axis perpendicular to the Earth's field at this point. We may have to watch it for just a minute here, but the thing that I want you to observe is the fact that its spin axis is tipping over in another direction. You see, now it's now tipped over to the point where it's almost facing the camera. And now it has. It's tipped about 90 degrees, but not toward the Earth's field, which is off to my right. Instead, it is tipped over towards the camera. I'll try that one more time. There it is spinning, and instead of tipping over toward the Earth's field, you can see it's beginning to tip toward the camera, precessing 90 degrees from the direction that it would have if it had not been spinning. There it's precessed about 90 degrees in those few seconds. And it will continue to spin right on around, to precess right on around in the direction that it's going.
We had another demonstration of the use of gyros on board Skylab in the backpack maneuvering unit we were testing. Operating this little maneuvering unit is every bit as much fun as it looks. It's intended for use in repairs outside the space station and is powered by those little gas thrusters you see, marked by black X's. As a working platform, it's rock steady, and it's kept that way by both sensing gyros and control gyros. Now I'd like to show you a final gyroscope in space. This little home of ours is spinning pretty slowly, only once every 24 hours. And it's also precessing. The torques exerted by the sun and the moon on the Earth's equatorial bulge cause the Earth's axis to precess in space with a period of about 26,000 years.